don't think it's where your immune system is attacking you. It's a reaction between that food and your cells. Whereas bacteria, they're more of a toxin that's destroying the cells.
So when we're talking about anaphylactic shock, is it the same kind?
Yeah, oh, that, yes.
Reaction?
Yes, it's the same kind of reaction. It's a toxin. It's an overwhelm. It's when your body can't stop it. It's so much that you go into shock. It's unable to be stopped, and you need outside help to do it. So that if you get anaphylactic shock from a food allergy, it'll be the same thing. Yes. What if your body is not suitable, or the environment is not suitable for bacteria? What can it do? Some do. How does it survive hundreds of thousands of years in King Tut's tomb?
In spores.
In spores, in endospores, exactly. Endospore is just a bacteria that takes its DNA knowledge, takes its vital parts, sticks it in a capsule, and then just sits there. Lets whatever goes on around it, wants dry, high acidity, weather, temperature, things of that effect, it just sits there. It's not a favorable environment, so it can't grow, so it'll just sit there. Wait till something happens. Weather changes, pH drops, rains, you inhale it into your nice, wet, warm mucous membrane. Then what happens to the spore?
It grows.
Opens up, knocks out that DNA, and starts to grow. Okay? When it goes into a spore, we call it sporulation. It goes from a bacteria. I don't think it's written in your book, but it is wise to write it down. Sporulation is when you go from a bacteria to a spore. When you get to favorable conditions and you go from a spore to a bacteria, we call that germination. So like a seed germinates, a spore going from spore to bacteria is called germination. Okay. So that makes sense? So which way is producing spores? Sporulation. Making spores. Making bacteria? Germination. Okay, exactly. So if you're in favorable conditions, you're going to have germination. If you're in unfavorable conditions, you're going to have sporulation. Okay, very good. Well, once we're in favorable conditions, and say you get sick, your doctor gives you antibiotics, 2 weeks of antibiotics, and you only take 4 days because you start feeling better. What are you doing to the bacteria?
Letting it learn what you just put into it so it can fight it later.
Yes. It's becoming what?
Immune?
Resistant. It's becoming resistant to that antibiotic. There's 3 ways that this can happen. Okay, first of all, if you do not kill off all the bacteria, some of them are going to gain knowledge on how to beat that antibiotic. Now it's going to transfer it to other bacteria so they can learn how to survive also. Okay? The first way that they're going to do it is through what we call a bacteriophage. They have it drawn like this in your book. Kind of think of it as a lunar landing pod. Okay. What happens is the DNA knowledge in here that just gained on how to.
What page are you looking at?
295. Transduction. Okay, this is genetic recombination. It doesn't have a picture of this on it. It has just a little picture of types of things. Think of it kind of this. What happens is this is called a bacteriophage, and it gets onto a bacteria, and it injects this DNA into here. This DNA is now going to combine with the DNA that's already there. Can you guys see that? Is that desk in the way? Okay, so it's going to combine with the DNA that's already there. And now this bacteria, usually few of these, what they'll do is they'll sacrifice themselves. We'll start to make a whole bunch of these. So it has a whole bunch of these. It's going to burst. All these are going to go out, find a new bacteria, and make it resistant. Once you have all these bacteria resistant, can you now use amoxicillin? Can you now use, let's see, MRSA is Michael what? What is MRSA? Methicillin resistant Staphylococcus aureus. So you can no longer use methicillin against this bug. You can no longer use some of these different antibiotics. We're on our 4th and 5th generation of antibiotics because people are making these bacteria non-effective. The antibiotics non-effective against them.
Is that true for like long-term antibiotics? So the same concept, like if you don't take it, if you stop taking it before it even has a chance to do anything, then it's not going to be effective anymore.
Yeah. And you really have to be careful with long-term antibiotics because they can kill your normal flora, and you have nothing there to protect yourself when you get a transient if you stop taking it. So you have to be careful. You usually have to taper off and get your good flora back in there through a process of either milks or dairies or different things like that that have them in it, honey, things like that. So yeah, you have to redo it. So transduction uses bacteriophages. That's the way in which this one is transmitted. It's called a bacteriophage. If the cell bursts, like this one blew up and has DNA fragments laying around, this other cell is going to come over here and it's going to pick up some of these DNA fragments. It could have fragments of the microbe. It could have fragments of the antibiotic. Not enough to kill it, kind of like we do vaccines when we're kids. We give a polio vaccine. We give a low dose of the actual disease, so we build up an immunity before it can actually make us sick. Things to that effect. That's how a lot of vaccines with children work. So you can get they can get vaccine, or they can get what am I trying to say? Vaccinated, more or less, to this antibiotic, or this antibiotic that killed the other bacteria. This is called transformation. So if it's a outside coming in, it's called transduction. If it's just the microbe itself picking up the DNA, it's transformation. Okay, and there's one last way in which these do it. It's through the F. pilus. Okay. What goes through the F. pilus?
Pieces of the chromosome,
Piece of the chromosome called plasmids.
Plasmids.
So the plasmid will be here. It'll go up through here and put it in there. This one is resistant. This one is now resistant. Okay, so it's conjugation. You've heard of conjugal visits. It's actual touching of bacteria. Okay, through the F. pilus.
So once a bacteria has become immune through transformation, can you then use conjunction to?
Yeah. It's either going to through transformation or through transduction.
Either one?
Correct. I want to see if you are, yes. Either way,
So wait, transduction is where it lands on it and injects the DNA, or?
It's where the bacteriophage lands on it and infects that first one.
Okay.
Now, it can either duplicate the bacteriophage and blow and put that out, or with the extra, the plasmid, it can now use conjugation to also get another bacteria resistant. Okay? So either it picks up the DNA or it gets through a bacteriophage. It can either use the bacteriophage or it can use the F. pelus. Does that make sense? So plasmids, we also call resistance transfer factors. On the bottom of 296, the second to last paragraph, it says plasmids are extrachromatic pieces of DNA in the cytoplasm of the bacteria. Bacteria often develop drug resistance through plasmids, also called resistant transfer factors. Something to be highlighted so that you, if they ask you what's another name for a plasmid, you can say resistance transfer factors. Okay. What is an antimicrobial?
Like an antibody or anti, my brain died, sorry.
Used to treat infectious microbial diseases.
Yeah, antimicrobial are going to treat, it's a broad word, it's like saying Japanese food. Okay, that's going to have a lot of stir fry and different other things in it. Okay, Japanese food is going to be the broad sense. Antimicrobials are going to be the broad sense. It's anything that we use to fight microbial infections. Okay, antibiotics are a form of antimicrobials. Does that make sense? Antibiotics are different because what? Highlighted or the italicized. They're derived from other organisms. Where do we get penicillin? Mold. Okay. We got our very first antibiotic from mold, which is actually a really funny story. You know how penicillin was discovered? Was he testing for penicillin? No, he was a sloppy scientist. A messy, sloppy scientist that allowed some of his samples to get contaminated by air, which had mold spores in them. And then he just left them, forgot about them. Came back, and where the mold had dropped on his plates, his agar plates, and on his samples, he had those clear ring zones of where the bacteria had died, where the mold was growing. And from there, he derived that mold had something in it that was killing this bacteria. He was then able to isolate penicillin, and we had antibiotics. So out of all you wives that have lazy husbands that don't clean up after themselves, it could lead to something very important. Just joking.
Messiness is a sign of genius.
There you go. Okay, so we have a couple spectrums of antibiotics.